We've been looking at a lot of examples where the quadratic function has real zeros, but it's not always going to be the case that your quadratic function only has real zeros. It could have complex zeros as well. So let's review what a complex number is and then talk about how to find those complex zeros. Now first, when we ask you to find the zeros of a function, as a reminder, what we're looking for is you're going to set the output of the function equal to 0, and then your responsibility is to find the corresponding x values that make the output 0. And then those x values are called the zeros of the function, or sometimes they're called the roots of the function. Now, when you are working with the quadratic formula, if the discriminant computes to something that's less than 0, that's an indicator that you're going to have some complex zeros. As a reminder, the discriminant in the quadratic formula is the part of the formula that is the b squared minus 4ac. All right, it's that part that's underneath that radical. Specifically, this part is called its radicand. So if b squared minus 4ac is less than 0, this then implies that you're going to have some complex zeros. So, quick review about what a complex number is. All right, so a complex number is a number that will be of the form a plus bi, where this I right here is called the imaginary unit. The imaginary unit I is defined to be the number such that I squared is equal to -1, or in other words, the number such that when you square it, you get a -1 out. Some people tend to remember this by remembering that if you take the square root of both sides, I is equal to the square root of -1. These are equivalent ideas. So your complex number will be of the form of a plus bi, where I is the imaginary unit. It kind of breaks it into the two parts. This first part, a, is called the real part, and this bi part is called the imaginary part. And it's probably important to note that in these complex numbers, a and b are real numbers. Okay, so they could be integers, they could be fractions, they could be decimals, they could be irrational, they could be irrational, all right, something inside that, the real number system. Speaking of the real number system, it's probably important to note that the real number system is a subset of the complex number system. Which means that every real number is actually also a complex number. So if you give me any real number, a, I can force this to be written as a complex number by writing it as a plus 0i. Okay, so all real numbers are also complex, but obviously then not all complex numbers are real. Alright, so now that we've kind of expanded away from the real numbers into the complex numbers, let's go find some zeros. So in this first example, the directions say find the complex zeros for each of these quadratic functions, and we're going to graph it and label the intercepts. Just as a heads up, we could drop this word complex in the directions. I could just say find the zeros of the quadratic function. The word complex is being thrown in there right now to remind you that we are allowing complex numbers to occur. So if you do get a complex number, I'll go ahead and work with it. But moving forward, sometimes we just say find the zeros, and that implies find all zeros. I don't care if they're real or complex, just find them. And then just as a reminder, this idea about zeros, you set your function output equal to 0, and we're going to find the corresponding input. Alright, so let's go ahead and do that. So for our first function, f of x is equal to x squared minus 4, where my function output is, I'm going to put a 0 in. So I have 0 is equal to x squared minus 4. And there's a couple different ways that you could solve this. I'm seeing that this is the difference of squares. Alright, so I'm just going to go ahead and use my factoring skills. So I get 0 is equal to x plus 2, x minus 2. Alright, so I set each one of those factors equal to 0 and then solve. If x plus 2 is equal to 0, that means x is equal to negative 2. If x minus 2 is equal to 0, that means x is equal to positive 2. Alright, so these that I just found, these are my zeros of my function. The x-intercepts of my function are going to be found by turning these into ordered pairs. So I have an x-intercept at negative 2, 0, and another one at 2, 0. So you can see that we have 2 real zeros and 2 x-intercepts. So don't get distracted if the directions say find the complex zeros and you only end up with real zeros, because remember, all real numbers are also complex. We could have also computed the discriminant. As a reminder is that b squared minus 4ac for this problem. So my b value is 0, so I would have 0 squared minus 4 times 1 times negative 4. Cleaning that up, I'll get positive 16. And the key thing right here is the sign. The fact that I ended up with a positive number for my discriminant tells me that I'm going to have 2 real zeros. Alright, so I've got my zeros, negative 2, 0, and 2, 0 as my x-intercepts. Let's find the y-intercepts. So as a reminder, we're going to put 0 in for x, so I get x squared minus 4, which just gives me negative 4, so that's the ordered pair 0, negative 4. And then looking at this, that'll also be my vertex. So maybe to help me finish graphing this, I'm going to get maybe just another point just to kind of see what this graph is doing after it gets past 2. So I'm going to be able to put an x being 3. So looking back at my function, I'll get 3 squared minus 4. That's 9 minus 4, which is 5. So that gets me the ordered pair 3, 5. That would be right here. And then I have, because of the symmetry, I have the corresponding point on the other side. So it just helps me finish out this graph. Alright, so there's the graph for the function. Okay, so we've seen things like that before, real zeros, nothing too exciting or fancy at this point. So let's extend this to kind of what the point of this section is about. So my second example, my function is g of x is equal to x squared plus 9. So first let's go ahead and find the zeros. So to find the zeros, we'll put 0 as the output. So I get 0 is equal to x squared plus 9. Now this is the sum of squares, which won't factor. We can only factor the difference of squares. So at this point in time, maybe we'll just use that square root property. So I'll subtract 9 from both sides. So I get negative 9 is equal to x squared. Let's go ahead and square root both sides to undo that square. Don't forget about your plus or minus. So on the right hand side, the square and the square root cancel, and I just get my variable out. And then over here on the left-hand side, to clean this up, just as a reminder, how do we clean up the square root of negative 9? We kind of think about it as two pieces. I think about what's going on with that negative, which I'm just going to attach to the number 1, and then what's happening to the number part. So the square root of negative 1 is I, and then the square root of 9 is 3. So what I get over here on this left-hand side is plus or minus 3i. We always kind of write the I part second behind the coefficient. So these are going to be my zeros. So I'm going to have positive 3i and negative 3i being my zeros. So my x-intercepts in this case, there aren't any. We could have seen that I was going to end up with complex zeros if we had found the discriminant. So for my discriminant again, which is the b squared minus 4ac, my b value here is 0, so I'll have 0 squared minus 4 times, my a is 1, and my c is 9. So cleaning this up, I'll get negative 36. And again, I'm not really too concerned about the number, I'm concerned about the sign. So because this is negative, this tells me I'm going to have two complex zeros. Okay, so we found our x-intercepts. We've actually found that there weren't any. Let's talk about now y-intercepts. So for the y-intercepts, we'll let x be 0, so the y value will be equal to 0 squared plus 9, which gives me an output of 9, so that's the ordered pair 0, 9. Then I can come over here and go ahead and graph. Now at this point in time, I only have the 1 point, so I'm going to need to get a couple more points in order to finish graphing this. So maybe let's explicitly talk about finding the vertex. So as a reminder, to find the vertex, the x-coordinate of the vertex is found by doing negative b over 2a. For this problem, it'll be negative 0 over 2 times 1. So that gives me 0 over 2, which is 0. And then looking at the x-coordinate being 0, that's actually what's going on right here. So I know this point that I just found right here, this 0, 9, is going to be my vertex. So let's maybe find some ordered pairs on one side of it, because this will also be my axis of symmetry right here. So if I find some ordered pairs on one side, I get to find the ordered pairs on the other side by just using the symmetry idea. So maybe I'll put 1 in for x. So I'll get 1 squared plus 9, which is 10. So 110, I can go ahead and graph that. Using symmetry, I can get the point on the other side. Maybe let's see if I can graph another point on this grid I've been provided. If I put x being 2, that'll be 2 squared plus 9, or 4 plus 9, which is 13. So that gives me the ordered pair 2, 13, which then I can get its corresponding ordered pair on the other side using that symmetry. And now we can have enough information to complete our parabola. Alright, there we go. So we don't have any x-intercepts, but I do have 2 zeros to this function, and we're able to kind of graph it using the y-intercept and a couple other ordered pairs. So we're seeing that we could start throwing in some complex zeros. That just means that we're not going to have any x-intercepts when we go to graph it, and we're going to have to maybe find some other ordered pairs to finish the graphing for the function. So here's going to be our last example. I would encourage you to try this example on your own, see how far you get, see what questions that you have where you get stuck. This is going to draw into some other stuff that we've seen previously, and also throwing in the possibility of a complex zero. See how far you get, and then go ahead and start playing this video and see how it helps you figure out the rest of the solution method. Alright, so the first thing for this then is we're going to find the zeros. So we're going to put, for my function, my f of x is equal to x squared minus 2x plus 5. We're going to set the function, the 0 as an output, and we're going to try to find the x values that make this true. Now looking at this thing is not going to factor nicely, so we'll just maybe use the quadratic formula. So as a reminder, the quadratic formula is negative b plus or minus the square root of b squared minus 4ac all over 2a. Anytime you're trying to commit a formula to memory, it's best when you're doing your homework, write it every single time, so that way it just starts becoming something that you repeatedly see. Let's start substituting in our values. So I'll get negative 2 plus or minus the square root of negative 2 squared. Don't forget about the parentheses when you substitute in that negative 2. Minus 4 times 1 times 5. Make that radical bar a little bit longer. Make sure we capture the entire radicand. Big long fraction bar here, and it's all over 2 times 1. Alright, let's clean this up. So out in front I'll just get 2 plus or minus the square root of, so this is going to give me 4 minus 20, so 4 minus 20 is negative 16, and then all over 2 times 1, which is 2. Alright, so I can see right here my discriminant is negative, so that implies I'm going to have 2 complex solutions. So let's find out what they are. The square root of negative 16, well, the negative is going to come out of the radical as an I, and then the square root of 16 is 4. So that's going to be 4i all over 2. And then I'm going to be able to simplify right here, because this number 2, the 4 and the 2, they all have something that divides them out, so they all are divided by 2. Remember, it's got to go into all 3 spots for you to be able to simplify right there. So this is just going to simplify to 1 plus or minus 2i. So my zeros are going to be 1 plus 2i and 1 minus 2i. And just as a fun side note right here, these solutions are conjugates of each other. As a reminder for what a conjugate is, the conjugate of a plus bi is a minus bi. So the real part is the same, the imaginary part is the same, but you're going to have a sign switch, and those two pieces are called conjugates of each other. So for every zero that you get that's complex, its conjugate is also going to be another 0 for the function. Right? So just fun fact. So those are going to be my zeros. Because they're complex, the x-intercepts, there are none. Let's find the y-intercepts. Okay, so we'll find f of 0. So again, for going back up here to my function, so I'm going to get 0 squared minus 2 times 0 plus 5. Right, so then I get my y-intercept as the ordered pair 0, 5, so I can go ahead and plot that. Alright, so I only have 1 point here, so that's really not going to help me too much to graph this. So let's go ahead and get some more information to graph it. Maybe we'll look for the vertex next. So for the vertex, remember the x-coordinate of the vertex is found at negative b over 2a, which will be negative 2 over 2 times 1. So I get 2 over 2, which is 1. Right, so that's the x-coordinate of the vertex. To find the y-coordinate of the vertex, we'll find f of 1. So that'll be 1 squared minus 2 times 1 plus 5. So that'll be 1 minus 2 plus 5, which is 4. So the vertex is then going to be the ordered pair 1, 4. So 1, 4, I can go ahead and plot that. Okay, that also then will tell me where my axis of symmetry lies. So if I wanted to, I could maybe put a dashed line in to indicate that. So I know I'm going to have this ordered pair over here at 2, 5 because of the symmetry, but maybe I'll just still get a couple more ordered pairs just to see how this parabola branches up to get a better idea of how it's going to finish. So coming back down here, maybe we'll try an x value being 3, so that'll be 3 squared minus 2 times 3 plus 5, so that's going to be 9 minus 6 plus 5, or 3 plus 5, which is 8. So then that gets me the ordered pair 3, 8. So I can come up here. Right, so 3, 8 is going to be another point on my graph. So I'm going to be able to use symmetry to get the corresponding point on the other side. And we have now lots of information to go ahead and finish graphing our parabola. So there we go. There's the graph of our function.